Okay, so I mentioned this on Friday, but now that we've proved with 6 things that triangles are congruent, I'm going to give you shortcuts so that you don't have to do 6 steps every time, okay? Instead, there's 2 that we're going to do today that use 3 steps. The first one is called the Side-Side-Side Postulate, which you are welcome to use as SSS every single time. You don't ever have to write side-side-side for me, okay? But the Side-Side-Side Postulate says this. It says if 3 sides of one triangle are congruent to 3 sides of another triangle, then those triangles will be congruent, okay? So on Friday, we said, just to be clear, all your sides, all your angles have to be congruent for the triangles to be congruent. Well, that will still be the case here. We just don't have to prove that the angles are, okay? So if the sides are, the angles will be as well, is essentially your shortcut, okay? So in this picture, what we would say is that triangle ABC is congruent to triangle, and here's the thing with these guys, you have to name them in corresponding order. So if I'm saying ABC, I'm going through the 1 hash mark, through the 2 hash marks when I name it. You have to do the same order when you name the next one, okay? Follow the same order. So DEF would be my order by SSS. Okay, so you'll say what triangles are congruent and which postulate got you there. You guys with me back there? Yeah? Okay, so that's the first shortcut that we're going to use. The reason this works is because triangles are rigid figures. And what we mean by rigid figures is if I took a triangle, right, and I just pushed on the side of it here, your triangle cannot rearrange to a different triangle with the same side lengths, right? If I were to push on that triangle, it's not going to get me a new triangle with the same sides. Okay, it gets me a totally new triangle. In other words, this would break if we pushed on it. Okay, can you think of a figure that doesn't do that? Like, is there a figure where if you push on it, your side lengths will stay the same? It's just going to look like a different figure now? A square would work. Pretty much, yeah, a parallelogram of any type, a quadrilateral, a 4-sided figure, a lot of 4-sided, would it be every 4-sided? I don't think it would work for every single one, but specifically, a parallelogram would work. If I had a figure that looked, say it started as a rectangle, right? If I were to push on the top of that rectangle, it's just gonna lean. Okay, I can keep these side lengths and these side lengths. It's just going to look like this now instead, right? Those are still the same length. Those are still the same length. It just leaned over, okay? That's not a rigid figure. It didn't keep its side lengths, its shape when the side lengths stayed the same. Yeah? Yeah, that's what I was thinking. I don't think it will work for a trapezoid. I don't think a trapezoid is a rigid figure because if it wouldn't stay a trapezoid. You could shift it and keep your side lengths. It would not stay a trapezoid, right? Yeah. Never really thought about that before until right as I was saying it to you guys. Okay, any questions on that? So the rigidity factor is what allows SSS to work out. There's no other triangle that you can make with 3 sets of side lengths that are congruent that will not make the triangles congruent, okay? Okay, so we're gonna do a couple proofs. The first one is this. Here's the thing with proofs, guys. You need to mark up what you know. So I gave you the markings here, but if they don't give you the markings, draw the figures and mark them up because that's what helps you get to where you need to be. So on this first one, it says LM is congruent to NP and LP is congruent to NM. So we know that information. Now, knowing what you just learned with SSS, what's the one thing we need to know is true? What?
Length.
The lengths of what?
And L.
Right, NL, that third side of both triangles is the only thing you need to be able to say, yep, those two triangles are congruent, right? So this is a very short proof. You have one extra little step in there other than proving the triangles themselves. What goes in that first gap? Given. So you're going to take all this information and you're going to put that here and call it given. Okay? Then you're going to say LN, the third side, has to be congruent to LN. Why? Reflexive. And here's why I would mark it. Okay? If you mark it, then you see I have side, side, side with side, side, side. So 2 is reflexive. And now we have the markings to use SSS. So we can say, and remember that last step of any proof is always whatever they asked you to prove. So triangle LMN is congruent to triangle NPL by what? SSS. Okay? The shortcuts come into play now. Questions on that? Okay, so that's SSS. The second one uses a term that I need to make sure you understand first. So we're going to first talk about the included angle. Think of it like if I want to be included, I want to be in the mix, right? I want to be right there. So an included angle is the angle that lies between the two sides that we're referring to. So like in this case, we would say angle A is included between which two segments?
BA and AC.
Right, segment AB and segment AC, right? It's the two segments that have A as part of them. Okay, so A is included between those two. So if I'm talking about these two segments, the included angle is the one that falls in between them. Okay? Okay, so what that does is that gets us to our next shortcut, which says this. This one's side angle side. Any guesses what letters we use for side angle side? SAS, right? So the SAS postulate says if two sides and the included angle of one triangle are congruent to two sides and the included angle of another triangle, then the triangles have to be congruent. Okay, so if you have an SAS setup that matches up with another SAS setup, those two triangles have to be congruent. Okay? Carson, you with me right now? So if you look at this picture, you have side, angle, side with side, angle, side. That means those two triangles are congruent. You don't need all three sides. You don't need all three sides and all three angles. You can just have side, included angle, side, and the triangles will be congruent. Okay, so this would be triangle ABC is congruent to triangle DEF. And again, you need to name them in the order that's the same as whatever you named the first one. So if I call this ABC, it has to be DEF. If I call it CAB, it has to be FDE. Okay, so match up the corresponding parts. And we would say they are congruent by side, angle, side. So by SAS. Okay, so rather than walk through an entire proof on this one, it's just going to be kind of a part of a proof. What do you need to know? So if you look at example 2 here, what other information would we need to prove that the two triangles are congruent by SAS? So we have one side. Is there anything else in this picture that you know is true? Yeah.
DF is congruent.
Right. So even though it's not marked for us, we know DF is congruent to DF. That's because that looks weird, huh? We'll just do this. So DF is reflexive, so we know that that is true. We need one more piece of information then to use SAS. Which angle would it be? if we were trying to use SAS? FDG and EFD, right? The included angles would have to be congruent. Now, here's my question. In this picture, do we know those angles are congruent? No, because they didn't tell us the lines were parallel. They're saying what would you need to need in order to prove it. They're not saying what is the proof. They're saying what extra piece of information do we need. So we need angle EFD to be congruent to FDG to be able to use SAS. Does that make sense? So reflexive, if it's there, you know that it's true, okay? We don't need DF to be proven congruent to DF on this because we know reflexive is always congruent, okay? What we don't know right now is that these two angles are congruent. So we would need to know those two angles are congruent to be able to say SAS, okay? Questions on that? Okay, last thing then. You have 4 pictures here. The question is, would you use SSS or SAS to prove the triangles are congruent? And then if you can, write the congruent statement. If there's not enough info, you just write NEI, not enough info, okay? So that first one, SSS, SAS, or not enough info? SSS. You have a side that corresponds to a side that corresponds to a side, and a side that corresponds to a side, right? So we can say the triangles are congruent. Here's the tricky part. Which triangles are congruent? So if I want to say triangle ABC, which triangle does that match up with? So I started at A, I went through the double hash mark, through the single hash mark. So where am I starting on the other triangle? You're starting at X, through the double, through the single would be XYZ. So ABC is congruent to XYZ by SSS. Okay, questions on that? Okay, how about the second one? Are those two triangles congruent? If so, by what? If not, why not? That would be SAS. You have a side that matches up with a side, an angle that's included, and then a side with a side. What's your congruent statement? Triangle what? I'll give you the first one. If I say ACB, which triangle does that match up with? QPR. That's a Q, sorry. By SAS, right? So I went through the first hash mark, through the second, so you need to go through the first, through the second to name it. Okay? All right, look at this one. Are those triangles congruent? By what? SSS or SAS, right? You have vertical angles here. So even though they're not marked congruent, vertical angles don't need to be marked. We know they're congruent. So your options are to say triangle ACB congruent to what triangle? If I say ACB, then I need to say ECD. Okay, and you may either say by SSS or you may say by SAS since you have vertical angles there. Okay? All right, last one. Are they congruent? Why not?
Because even though one left works, one right doesn't, since the angles of length.
Right. So if you look at this one, it goes side, angle, side. This one is not the included angle. This would be the included angle, and we didn't get that one, right? So this one you have an angle, and then a side, and I'm gonna tell you something inappropriate here because it's gonna help you remember this down the road. There is no swearing at your teacher, right? We call this the Donkey Theorem. Sure, you can imagine why. It does not exist. So if you see ASS or even backwards of that, it doesn't work ever, okay? That's not true. There is one situation that it works, but we don't call it ASS because it's something else. And I will explain that to you in a few days. But just know I should never swear at my teacher, therefore I will never write the word ass on my paper. Deal? Okay. I do that for you and for me. I don't want to be sworn at, but you don't want to get the question wrong. If you write ASS, it's wrong. Okay, so for this one, because that doesn't work, we would just say NEI, there is not enough information. Those might be congruent triangles, but with the markings they gave us, we don't have enough information to say yes, they are. Okay, so you say not enough info, and that is it. Any questions? Yes, sir.
Can you go back up to the bottom of the first page?
I don't remember where the bottom of the first page was. Right there? Yeah?
Yeah.
Okay.